Hey everyone, and welcome. If you've ever bought a new computer and kind of squinted at the specs thinking, wait a second, the clock speed is barely higher than my PC from years ago, you are definitely not alone. For a while now, it feels like we've hit a wall. So let's dig in and figure out why we seem to be stuck on this gigahertz plateau.
This is really the core question, isn't it? It's something a lot of us have noticed. Those huge, exciting jumps in pure clock speed that we got used to in the 90s and early 2000s, well, they just sort of fizzled out. So what happened? Did we just hit some fundamental physical barrier?
Now, the first thing you might think of is the speed of electricity itself. We all learned that it's basically the speed of light. But, and this is a huge but, it's a bit more complicated than that. You see, the electrical signal, that wave of energy, is absolutely screaming fast. But the electrons themselves, the little particles actually carrying the charge, they're just kind of drifting along, surprisingly slowly. And that little detail is our first major clue.
Okay, so to really get to the bottom of this bottleneck, we have to zoom in. I mean, way in. We need to get down to the level of the single most important building block of any modern chip, the transistor.
And when I say we're zooming in, I'm not talking about looking at a few hundred of these things. We're talking about billions, literally billions of these microscopic switches crammed onto a piece of silicon smaller than your thumbnail, all flipping on and off billions of times every single second. The scale is just, it's mind-boggling.
So what's each one of these billions of transistors actually doing? Well, at its heart, its job is pretty simple. It acts like a tiny battery that has to charge up to turn on and then discharge to turn off. The faster you can make it do that charge-discharge cycle, the faster your processor is. But there's a huge catch. Every time it switches, it kicks off a tiny puff of heat. Now, multiply that by billions of transistors, switching billions of times a second, and suddenly heat isn't just a byproduct, it's the #1 enemy. So yeah, that heat problem is a massive deal, but it's actually tied to something even more fundamental, a physical speed limit that's baked right into the materials we use to build our processors. All right, here's the key term for today. It's called saturation velocity, or VSAT for short. The easiest way to think about it is like the top speed of a car. You can floor the gas pedal, you can push it as hard as you can, but the engine and aerodynamics mean it's just not going to go any faster. That's VSAT for an electron in a material like silicon. It's the absolute top speed, no matter how much more power you pump in.
And what's really interesting is that this speed limit is different for every material. It's not some universal constant. This table shows that for silicon, the material we've relied on for decades, that top speed is about 1 × 10⁷ centimeters per second. You can see other materials like germanium or gallium arsenide have their own limits. The key thing, though, is that every material has a ceiling.
So, you might be wondering, okay, that's a cool theory, but how do we know it's real? Well, scientists test it constantly. This graph is a perfect example. The solid line is the mathematical model predicting what the electron speed should be, and those little black squares? That's the data from actual real-world experiments. The fact that they line up almost perfectly tells us, yeah, this speed limit is very real.
Okay, so there's a hard physical limit, a rule. End of story, right? We pack up and go home. Well, not quite. Turns out, physics is weird and has some pretty sneaky loopholes. We just established this, right? Saturation velocity is the top speed. It's a fundamental rule of the road for electrons inside a semiconductor. But what if you could break that rule, just for a tiny fraction of a second?
And this is where it gets really cool. The phenomenon is called velocity overshoot. For unbelievably short distances, we're talking nanometers here, an electron can actually accelerate past its normal top speed. Remember that car analogy? Imagine, for a split second, you could hit the nitrous button and the car's RPMs scream past the red line. That's what engineers figured out how to do inside a transistor, harnessing that brief, rule-breaking burst of speed to make switches just a little bit faster.
So for years, engineers have been absolute masters at using that little nitrous boost of velocity overshoot in smaller and smaller transistors. But to get the next really big leap forward, you don't just need a trick, you need a whole new car with a much higher top speed to begin with. And that means looking beyond good old silicon.
And that brings us to graphene. You've probably heard about it. It's this wonder material, a single layer of carbon atoms in a perfect honeycomb pattern. The reason scientists and engineers are so excited about it is that its built-in speed limit, its intrinsic saturation velocity, is just way higher than silicon's.
So the dream is to build these things, graphene field effect transistors, or GFETs. The potential is enormous, but
That graph on the right tells a familiar story, a story of incredible promise that runs smack into our old nemesis.
Heat. That's right. This chart is absolutely fascinating because it shows just how brutal the laws of physics can be. In a perfect theoretical world, a graphene transistor could hit blistering speeds, around 60 gigahertz. But once you factor in the heat that the transistor generates itself, what they call self-heating, look at that drop. Performance plummets by a third. So even with a faster material, we are still fighting the exact same battle.
And that really brings us to the heart of the matter. The reason we're stuck around 5 gigahertz isn't one single thing. It's not one wall. It's a dozen different problems all at once. It's an incredibly delicate balancing act.
It's a giant game of trade-offs. It's like you push on a balloon here and it just bulges out over there. You want to make the transistors switch faster? Boom, you generate more heat. So you try to make them smaller? Great. But now they start to leak electricity and have more resistance. Okay, so maybe make the whole chip bigger? Nope, because then it literally takes too long for the electrical signals to get from one side to the other. Every potential solution creates another problem.
Which leads to this quote from an engineer that just nails it. There isn't a single limiting factor, there are a set of trade-offs that bound what can be achieved. And that's the answer. We're not up against a single wall. We're boxed in from all sides. And that's exactly why the entire industry shifted its strategy. The game stopped being about how fast can we go, and started being about how smart can we be, leading to more cores and specialized chips for specific jobs. So the real question for the future is, what do you think that next clever trick is going to be?